Okay, yes, guys. Hi, very good evening, everyone. Welcome once again to Om Institute and welcome back to the Champion Series, the GATE 2025 Champion Series. Okay, to cover up the very important topics for GATE. So, last session that I took on control systems was about the Nyquist stability criteria, explaining the Nyquist stability criteria specifically in detail. Okay. Now, again, as per students' demand and observation, the next topic that I'm picking up is controllability and observability. Of course, an important topic, and some students also message me personally that this is, what they want to even get more command on this topic, controllability, observability. So let's learn, okay, the rules of controllability and observability in this particular session. Personally, that this is, what if. So yeah, I definitely feel the audio video is good. Let's get moving ahead, okay, with the concept of controllability and observability straight away. Okay, right. So, big updates for you. Okay, before I start up the content, that yes, the All India GATE 2025 mega free mock test, mega online free mock test. Yes, guys. Okay, feel the gate before the GATE examination. Feel the gate before the GATE examination. So, an All India Open mega mock free test for all GATE 2025 aspirants from Home Institute, 12th January 2025. The timing 2:30 p.m. to 5:30 p.m. Okay, and there is specially exciting gifts for the top 5 students. Okay, of course, there will be All India performance given, All India ranking, real time experience, just like GATE, and detailed explanation for all the questions. Okay, of course, mode is online because GATE is itself online, and the streams EC and Triple E. Okay, you can also scan here. The QR code has been attached. So if you want to, register for this mega mock test, okay, you can just scan this and you can register. It takes very few seconds to complete this. For any more details, you can contact 95156 94053. Okay, 95156 94053. Also, guys, the GATE 2025, the first, okay, offline batch. Again, a big announcement. The first offline batch for GATE 2026 is going to be, okay, from 24th of February, offline live at our Hyderabad center. Okay, the fee 65,999 is currently priced as 54,999 with special discounts for different category of students. And also, if you register till 30th of January, okay, you get a special early bird discount of 4,000 over and above this fees mentioned 54,999. Right, guys? So let's get moving ahead. Okay, let's get moving ahead. Okay, and let's talk about, okay, let's talk about this particular system. Okay, let's talk about this particular system. Okay, where, if I take a nth order control system, if I specifically take up a nth order control system, which will be described by n state variables, which will be described by the n state variables, which will be described respectively by n state variables. Just some basic terminology review let me have before I start the controllability and observability. Okay, let's say ut is the input and yt is the output of the control system. Okay, assume it to be SISO initially. Okay, now how do we write down the equations governing the state space model? Whenever you talk about state space model, dear, whenever you talk about state space model, in short, I keep calling it as SSM. Okay, some basic terms to be reviewed. Okay, because we are not covering the entire state space analysis in today's class, but of course, the concept of controllability and observability, 2 special tests we learn, Kalman's test and Gilbert's test. Okay, that will make, all varieties of your problem covered up, mixed with some shortcuts. Okay, the state space model, okay, comprises of state equations, SE, and the output equation. The state equations and the output equations. Output equations, OE. Okay, given by, now state equations being given by the relation x dot is equal to ax plus bu. Okay, and y is cx plus du. So as I already mentioned, u is the input and y is the output. Okay, for MIMO, the u becomes input vector and y becomes the output vector. Okay, x is the state vector. X is the n cross 1 state vector. which contains all the state variables. Column vector arranging all the state variables of the system. x1t, x2t, etc. up to the xnt. Okay, that is what is the n cross 1 state vector. This is what we call it as the n cross 1 state vector. Okay, in a general sense, you should also basically have the idea about the size of the matrices. Okay, idea about the size of the matrices. Okay, so if I just generally write down the sizes of these matrices, okay, x dot is equal to ax plus bu. As I mentioned, this is n cross 1. X dot means the derivative, of course, derivative of the state vector. It also has n cross 1. A is the system matrix, n cross n size. Now u, if I generally assume MIMO, then we can also convert to SISO also. Okay, generally if I take MIMO case now, multiple input, multiple output, to u here, okay, u here means UT, and UT means input vector basically. U here, not the single input, it means the input vector. What is the input vector UT? Okay, it is the column vector containing all the inputs. Okay, so suppose I have P inputs. Okay, suppose I have P inputs applied to the system. So this becomes P cross 1. Okay, U will be of the size of P cross 1. Okay, and B then is of the size N cross P. Okay, similarly, if I talk about the output, okay, now if I talk about MIMO system again, Y or YT, okay, would mean the output vector. Okay, and that is again a column vector containing all the outputs. And let us assume that the system has Q outputs. So this is a vector of the size Q cross 1. Now, what is the output equation? I told you output equation is written as Y equal to Cx plus du. Okay, where X, I already told you, is the state vector n cross 1. Okay, Y is the output vector Q cross 1, and U is the input vector, multiple input case, so that is P cross 1. C is then given by the size Q cross n, and D is then given by the size Q cross P. Right. These are general, this is just general state space model introduction. Okay. Before I start controllability and observability. Okay, my main focus, because covering up state space models, everything, state space models, solving them, different varieties will take a lot of time. But in this session, I'm confined to an important topic of controllability and observability. Okay, now, what is controllability? Okay, whether a system is controllable or not. Okay, if a system is controllable, you should be able to control the entire state of the system. Okay, that means you should be able to control all the state variables of the system. So we say that a system is controllable if you can control all the state variables of the system. Now, how you can control? A system has been designed, say for example, okay, you can apply the input and you can measure the output. That's what you can do. Now, suppose the system has been designed and packed in a black box. It has been designed. Okay, nth order system has been designed, packed in a box. It has n state variables x1 to xn. Okay, so what a user can do? User can apply some input and user can measure some particular output. That's what a user can specifically do. Correct, dear? Okay, so if by applying a particular input, if you are able to control all the state variables of the system, then the system is said to be controllable. Okay, a system is controllable if all the state variables can be controlled to reach a specific value. By how? Of course, by applying an input. Even if there is one state variable which cannot be controlled, then the system is overall said to be uncontrollable. Okay, uncontrollable. Okay. Now, similarly, you applied the input to control the system, okay, or to obtain some output. Okay, so you applied the particular input to a system. Now, at any point of time, you are interested in measuring what is actually happening. You want to observe the system, okay, whether the output obtained at any particular time, okay, is correct or not. You want to have the complete details inside of the system at any point of time before the operation is completed, before the process is completed. Okay, so you want to observe the system. And how do you observe the system? By observing the state variables, because What is the concept of state variables? State variables are set of those variables which completely describe a control system. Okay, every information, okay, at any point of time is hidden inside the state variables. So if you want to observe a system, means you can observe the state variables. And how you can observe? Input was applied some time back. At any point of time you want to observe the state variables. So what you can do at that point of time, you can measure the output. Okay, and by the knowledge of the output, are you able to sense? By the knowledge of that output, are you able to sense or are you able to observe all the state variables? If yes, if you are able to observe all the state variables, then the system is said to be observable. A system is observable if all the state variables of the system can be observed. By how? Again, by measuring the output. Okay. Now, truly it depends, okay, whether a system is controllable or not. It truly depends on these equations. Okay, what is the state equation and what is the output equation? Okay, whether or not by the measurement of output all the state variables can be observed or not. Okay, but what you have to do, you don't have to check the inputs. You don't have to check these equations actually. Okay, rather you will have to apply the methods which I am going to talk about in this particular session. Derivation not required. Okay, your focus is conquering questions right now. GATE exam is very close, and the first test, the general test of controllability and observability, is in the form of Kalman's test. It is in the form of Kalman's test, the Kalman's test of controllability and observability. Okay, so again, there is a system given by x dot equal to ax plus bu, state equation, y equal to cx plus du, output equation. What is the Kalman's test? Let me first tell the controllability test. Okay, let me first talk about the controllability test, and then let's apply to the questions also. A system is controllable. A system is said to be controllable if the following controllability matrix has a rank of n. Okay, so I define a controllability matrix. Okay, a controllability matrix having the rank, it should have the rank n. A controllability matrix such that it should have the rank n. Okay, some typo error is there. Better I will write it once again. No issues. S. What is that controllability matrix? It contains augmented matrix B, AB, A square B, A cube B, etc. up to A power n minus 1 into B. I use the word right now. Dear, I use the word right now. Augmented matrix. Augmented matrix. Good evening, Raj. Sir, I will write it once again. What is that controllability matrix? It contains augmented matrix B, AB. Okay, yeah. Right. So, what I mean, I just use the word right now, augmented matrix. What is that augmented matrix? When several matrices are combined and written inside a single matrix. That is what augmented matrix. So what I am doing, the matrix B, along with that AB, A square B, etc., up to A power n minus 1 into B, all written inside a single matrix known as the S, known as the controllability matrix. Okay, dear, in general, what is the size of this controllability matrix? So just now I told you that, okay, what is the size of the matrix B? See, if I talk about the B matrix, what is the size of the B matrix? Is n cross P. I just now told you the B matrix. Okay, that is of the size n cross P. Here it is, n cross P. A is n cross n. So when you talk about C, B is n cross P. If you talk about AB, okay, now see A is n cross n, B is n cross P. Okay, they can be multiplied because the number of columns of second is equal to number of rows, number of columns of the first is number of rows of second, and the final output is given by n cross P, first cross lost. The rows of first multiplied by columns of second, that is n cross P, correct? That is n cross P. So now this is n cross P, this is also n cross P. Similarly, next will also be, you see, n cross P. All of these matrices will be n cross P, and you are arranging them one after the other horizontally. That means you're not increasing the number of rows. What you are increasing is number of columns. What you are increasing is the number of columns. So overall size of this matrix is, okay, you are not going down. The number of rows is n fixed. For each of them, number of rows n, but columns is p n times p n times, that is n cross np. Okay, so first we have to form some controllability matrix S. Now, as per the Kalman's test, a system is controllable if this controllability matrix has rank n. Calculations I will explain you more with question, n cross np. But specifically, if I also take a SISO case, SISO, single input. SISO means single input. So P equal to 1. Okay, P equal to 1. And if P equal to 1, then the matrix S, dear, becomes n cross n. If P equal to 1, N cross N means square matrix. Okay. Okay, so if the question is concerned on a square matrix, the result is very simple, because for a n cross n square matrix, to have rank n, full rank, okay, to have the rank n, that is the full rank condition. Okay, what is the condition? You know, linear algebra. You just have to revise the basic linear algebra. For a n cross n square matrix to have the rank n, it should have non-zero determinant. It should be a non-singular matrix. So in the SISO case, it basically turns out to be a determinant calculation. If determinant S not equal to 0, system will be controllable. If determinant S equal to 0, it is not controllable. Simple. Okay. Right. Yeah, that is what I've mentioned here once again. Okay, for SISO system, we need mod S not equal to 0, controllability matrix being non-singular. Okay. Now, dear, observability test. Let me write down the observability test also and then take up the questions. Right. Have a look into this. A system will be observable if the following observability matrix has a rank of n. Okay, following observability matrix has rank n. Okay, now see the observability matrix formed by CA square, CA power n minus 1, where we already discussed C is some matrix which is given by Q cross n. Okay, C is the matrix given by Q cross n. So see, what is going to be CA? Okay, what is going to be C into A? Let us see this calculation here. Okay, the size of CA. Okay, so C, as I told you, is Q cross n and A is n cross n. Okay, so the final size will be first cross last, that is Q cross n. Okay, so this will also be Q cross n. Similarly, if you try CA square will also be Q cross n up to CA power n minus 1. All of this actually will be Q cross n, and this time you are writing one below the other. This time the arrangement is one below the other. That means what you are increasing is number of columns. Number of rows. What you are increasing is number of rows. How many rows? Q, n times. So that is NQ. Cross. The columns are fixed. N columns. Okay, the columns are fixed only. Okay, you're going down, the number of rows will increase, but all of them are limited, having n columns. Okay, so V is generally of the size NQ cross n, but once again, if you take SISO consideration, if you take SISO, single input, single output, so single output means Q equal to 1. Okay, and single output, because it means Q equal to 1, V again becomes n cross n. That means again it becomes a square matrix. The observability matrix will also be square in case of SISO system, and for rank of V equal to n. Okay, that means again full rank condition. The determinant V not equal to 0. Okay, so for SISO you have simple conditions. Determinant V not equal to 0. Okay, same thing I've mentioned here once again. Observability matrix must be non-singular. And here, let me first apply this test for a second order system. Then slowly we will go to the third order. Let us apply this to the second order first of all. The determinant V not equal. Okay, everyone. Okay, so first of all, let us write this in the matrix structure. What is given? X dot equal to x1 plus x2 plus u, and x2 dot is equal to minus x2, and y is equal to the x1. Okay, x1 dot, x2 dot, arranging them in the column vector form, is equal to ax. Okay, x means the state vector containing both the state variables x1, x2 plus bu. Okay, and y equal to cx, that is c x1, x2 plus du. There is no input term. Okay, so that is clearly 0. Y equal to cx. Clear? Now, first equation, what is x1 dot? X1 plus x2. That means the coefficient of x1, x2 both 1. Okay, plus u. Okay, so plus u. The input is also coming in the first equation. Second equation, x2 dot is minus x2. Okay, no x1 in the second equation, only minus of x2. So x2 coefficient is minus 1. Okay, and plus u. Okay, plus 0 into u. And y equal to x1, x2. Y equal to 1, 0, x1, x2. Y equal to 1, 0, x1, x2. Y equal to cx. Clear? Y equal to the cx. Done. Done. This is what it is. This is what it is. Clear? All right. Okay. Now, observability and controllability both required. Let us start with the controllability calculations. let us start with the controllability test. Now see dear, controllability matrix S is given by B, AB up to A power n minus 1 into B. But what is the type of system right now? It is a second order system. It is a second order system, n equal to 2. If n is equal to 2, S will only have what part? B and AB. Okay, A power n minus 1. N minus 1 itself is 1. So up to AB only. Up to AB only. Okay, out of which B matrix is given to me. Okay, so what is the AB matrix? Only thing is, what is the AB matrix? So B matrix, let me write down the B also. Okay, so B is 1, 0. What about the AB matrix? So a basic multiplication I will do. This is B matrix and A matrix is 1, 1, 0, minus 1. Let me multiply. First row, first column 1 and 0. So that is 1. Then second 0 and 0. So this is 0. Okay, so what is the final answer? Have a look into this. What is the final answer? B is 1, 0. AB again is 1, 0. Okay, this is the S matrix. Now, what is the determinant of the S matrix? Okay, so yes, we have some answers coming up. Okay, NS is not controllable but observable. Okay, chalo, good going. So, what is the determinant of this matrix? Entire row is 0, so determinant is 100% 0, and determinant 100% 0, telling you that the system is not controllable. Okay, the system is uncontrollable. Clear? The system is uncontrollable. Done. This system is uncontrollable. Okay. Next, observability test. Next is observability test. Okay. For the same question, observability. Okay. Now, dear, what is the V matrix? V matrix is in general given by C, CA, etc. up to CA power n minus 1. Okay. But because n is 2, again it is a second order system. Okay, so n minus 1 itself is 1. So up to CA only, CA. Out of which C matrix is given to me. C matrix is this one, 1, 0, y equal to Cx. So C matrix is 1, 0. Okay, let me do the separate calculation here. C matrix is 1, 0 given. What I need is the CA product now. So C is 1, 0 multiplied by A matrix. Multiplying now, dear, first row, first column. So 1 into 1 plus 0 into 0, 1. 1 into 1 and then again 0. So 1, 1. Okay, what is this answer? 1, 1. Okay, now what is the determinant of V? Okay, what is the determinant of V? This time you see clearly, cross multiply 1 into 1. Okay, minus 0. So answer is 1. More important, answer is non-zero. Observability matrix is non-singular, non-zero determinant. So the system is observable. So the system is observable. It is not controllable but observable. It is not controllable but observable. This is the final concluding remarks for the question. This one is not controllable but observable. Okay. Now next question. Let's solve the next question. Okay. And slowly, let's introduce some techniques and tricks also within the question. Okay. X1 dot is X2. X2 dot is minus 2x1 minus 3x2 plus u and y equal to x1. Okay, let's do it. Okay, first let's convert this into the matrix form. Okay, so once you convert this into the matrix form, x1 dot x2 dot is equal to ax plus bu, y equal to Cx, y equal to the Cx. Okay, y is equal to the Cx. Done. Now see, x1 dot is only equal to x2. x1 dot is only x2, no x1. Okay, so 0, 1 coefficient. x2 dot is minus 2x1 minus 3x2. Acha, in the first equation there is no input term also, so 0. In the second, minus 2x1, so x1 coefficient minus 2, minus 3x2, so next is minus 3 plus u. Okay, so input coefficient 1. Okay, and then y equal to Cx. Okay, y is equal to the Cx. Okay, so what is y? 1, only x1, y equal to only x1, so 1 and 0, no x2, so y is 1, 0, y is 1, 0, x1, x2. Okay, now dear, I will solve the controllability test for you, but if you observe what type of state space model it is, if you actually observe what type of state space model it is, you should be able to get your answers even more quickly. I will tell you what type of special state space model. Can you observe, guys, if you have completed state space model? Okay, can you observe this? Okay, so let us start. For controllability, we need the controllability matrix. It is second order system. That means up to AB. AB. Okay, what is B? B is 0, 1. And what is the AB? Let me calculate the AB here. Okay, let me calculate the AB here separately. Multiplied by B, what is the result? 0 and 1. 1, then 0 and minus 3. Okay, so what is the AB? 1 and minus 3. Now check the determinant. Last calculation. Determinant, cross multiply 0 minus 1. Minus 1 not equal to 0. Determinant not equal to 0 confirms that yes, the system is controllable. It is controllable. It is controllable. All right. Yes. So Anas says answer controllable and observable. More important is the form I was looking. CCF form. Yes, guys. This is what is actually the CCF form of the state space model. The CCF form of the state space model. Controllable canonical form. We name it as controllable canonical form because such a form is always controllable. Controllable canonical form. If you identify these basic forms, okay. If you identify the basic forms, let me give you a quick review. Okay. Let me give you a quick review of this. Okay. The different ways. Okay. The different standard state space models. Okay. The different standard state space model. The standard state space model. Because state space model of a system is not unique. There can be thousands of ways of expressing a system. Okay. The four important ones are standard forms are CCF, controllable canonical form, because such a form is always controllable. Okay. Such a form is always controllable. I'm just giving you that review how to identify CCF, Rishabh. Coming to that only. OCF, observable canonical form. Such a form will be always observable. Okay. Then there are two normal forms. DCF, diagonal canonical form. JCF, Jordan's canonical form. How to identify? I'll give you a quick review, a quick revision of that. Suppose if I come for a second order system, giving you the highlights first about the second order system. Y by U equal to B, C1S plus C0 upon S square plus A1S plus A0. Okay. See, denominator, the highest power of S is 2. It's a second order case, correct? This is what is a second order system for you. Okay. Now here, just have a look into this. Okay. What is the CCF representation for it? What is the CCF representation? X dot is equal to AX. These are standard forms actually. These are standard forms. It's better to remember them always because a lot of questions will be using this standard form knowledge to save your time actually. Okay. So X dot is AX plus BU, Y equal to CX plus DU. There is no D. D will always be 0 here. Okay. What is the structure of the A matrix? First row 0, 1. Okay. Second minus A0 minus A1. Now what is A0 A1? Okay, what is A0 A1? Okay, the coefficients in the denominator starting from constant, that is starting in the reverse manners. So write down A0 A1 with opposite sign plus 0 BU. What is B? B if there is any common term in the numerator. Y equal to C0 C1. What is C0 C1? What is C0 C1? Okay, C0 means C0 C1 are the coefficients of the numerator starting from constant. Okay, C0 C1 but same sign. Okay, but same sign. Okay, let's understand more through numbers. Let's understand more through numbers. If I write down an example, okay, suppose you are given transfer function of any system, say for example, 2s plus 6 divided by s square plus 5s plus 8, something of this kind. Okay, what is the CCF state space model for this? Okay, what is the CCF state space model for this? So, it will be given by the answer. See dear, everybody just follow with me. Okay, X dot is AX plus BU. Okay, and Y equal to CX. What is the A matrix? What is the A matrix? As I told you, first row is always 0, 1. First row will always be 0, 1. And second row, okay, so look into the denominator. Start from the constant. Go reverse, 8 and 5 and opposite sign. Okay, so 0, 1, minus 8, minus 5. Plus, now numerator can, if you want, you can take 2 common. If you want, you can take 2 common. Okay, so this common term is known as the b. I told you, 0b. Okay, this b here is 2. Okay, then what is C naught C1? Y equal to Cx, C naught C1. C naught means constant. Again, go to the numerator, start with the constant term, that is 3. And next coefficient is 1, same sign. Okay, here same sign, only sign change in the A naught A1 term. Correct? This is what should be the CCF form. Okay, this is what should be the CCF form. If you want to write down OCF form, see, just remembering one form, CCF or OCF, remembering one form is enough. I'll show you. If you want to write down the OCF, don't remember any separate result. Don't remember any separate result. I will just tell you the simple way of writing the OCF form. A very simple way of writing the OCF. CCF being more common, remember CCF, and OCF just remember by a simple technique. Whatever is the A matrix here, take the transpose here. Take the transpose to 0. Transpose means the row becomes column. The first column 0, 1, and then second row becomes second column. So minus 8, minus 5. Now whatever is B, take the transpose and write down in place of C. So row becomes, this is column, column becomes row, 0, 2. B transpose going to C, and whatever is C, take the transpose and go to the B. Okay, so this is column row 3, 1, make it as column 3, 1, and this goes to the C. This is what exactly has been written here also. Okay, A matrix of OCF is A transpose of CCF. B of OCF is C transpose of CCF, and C of OCF is B transpose of the CCF. B transpose of the CCF. Correct, dear? Okay, correct, dear. This is what is the CCF form. Okay, and OCF form for second order. If I give you third order, okay, have a look into a third order example. Denominator starts with S cube plus A2S square plus A1S plus A naught. And the numerator is B, C2S square plus C1S plus C naught. Okay, got it? Good, good, good. Now see, what is the CCF for this? Okay, now, because it is a third order system, A matrix will also be a 3 cross 3 matrix. Look into the last row, and then I will explain you rest of the things. Look into the last row. How it starts? A naught, again the constant of the numerator, and go reverse. A naught, A1, A2, an opposite sign. A naught, A1, A2, opposite sign. Clear, everyone? Okay. Plus BU. I will explain this part. Forget. Look into the last row. Now plus BU. B is 0, 0, B. Only last element will be non-zero. And what is that B? Again some common in the numerator. Again some common in the numerator. And what is Y? CX. What is C naught, C1, C2? Same pattern here. Go to the numerator, start with the constant term and go reverse. C1 and then C2. C naught, C1, C2, same sign. Numerator terms, same sign. Denominator terms, opposite sign. Minus A naught, minus A1 and minus A2. Now, look into the upper part. See, what is going to happen is, okay, last row is fixed. That is coming from denominator. Now go above. The first column entries will be all 0. Okay, the first column entry will be all zeros here. And this particular term will be a 2 cross 2 identity matrix. Isn't it identity matrix? Diagonal elements 1, 1, rest all 0. Okay, rest all 0. Okay. Understand more again with a number. Understand more with the numbers. Okay. So suppose I give you an example. Suppose you want to write down the CCF answer. Here. Suppose you want to write down the CCF answer for, S square plus 3S plus 5 divided by S cube plus 2S plus 6. Something of this kind. Something of this kind. Okay. So what is the CCF answer for this? I want to write down the CCF answer for this. Okay. X dot is equal to AX. A will be 3 cross 3 matrix. Okay. Plus BU. Okay, Y equal to CX. B means 0, 0, B. What is any common? So this time I cannot take anything common. So B means 1 here. B means 1 here. Okay, no common term. So it is simply 1. Now Y equal to C naught, C1, C2. What is C naught? Common. The constant of numerator. 5. Then go reverse 3 and then 1. Same sign, 5, 3, 1. Now come to the A matrix here. Come to the A matrix, okay, and fix the last row. How the last row will start? Again by the constant term 6 and then 2 and then opposite sign, of course, and then what? 6, 2 and then not 1. See, S square is missing. S square is missing means you can assume here 0 into S square. So next coefficient is 0. Don't do the mistake. Don't take it as 1. Okay, S square is actually missing here. So 0. And then opposite sign, minus 6, minus 2, minus 0 is same as 0. And then the first column, rest of the first column entries, 0, all zeros, and then identity matrix. Identity matrix. Done, dear? Okay. So this is what a CCF, and then, dear, if you are done with CCF, for the same system, OCF, you will write on your own. For the same system, write on the OCF on your own. Okay, simple activity, simple homework. Take the transpose of this matrix. B transpose you take, that will go to the C. C transpose you take, that will go to the B. Simple rules I told you already. Okay, the general answer is already written in front of you. Okay, now let's come back to our discussion. Okay, and 2 more forms I will review. I will review DCF and JCF later once I go to the Gilbert's test. Okay, so dear, we were solving some questions. Let us come to this question again. As I told you, if you observe, okay, 0, 1 minus A0 minus A1. Okay, plus 0 BU, y equal to C0 C1x. Okay, it is the CCF form. So why to check controllability? CCF form always controllable. CCF form always controllable. Even if you check 110% controllable. So if you can check that it is a CCF form, no need to check controllability. And then for CCF form, there is a shortcut for observability also. How? Okay, first let us test it. First, let us check it. Let us check on our own. First, let us confirm. Okay, first let us confirm. Okay, for observability, we need the matrix V, which is CCA. Second order, so only up to CA. Okay, dear, what is the C term? What is the C matrix of the question? Is 1, 0. And what is the CA matrix? Okay, let me multiply here. CA, C is 1, 0. A is 0, 1, minus 2, minus 3. Multiplying it, what do I get? First row, first column, 1 into 0, 0 into minus 2, 0. Then first row, second column, 1, then 0. This is 1. Okay, so this is 0, 1 here. Okay, now what is the determinant of V? Determinant of V is 1 minus 0, which is 1. That means not equal to 0. Determinant not equal to 0. The system is observable. So it is controllable and observable. I have done by Kalman's test. Okay, but the system can be directly said as controllable because of the CCF form. Observability shortcut for CCF form, I will tell you. Just wait, let's solve one more question and then I'll tell you the observability shortcut. Okay, another question for you. Okay, let me write down in the matrix form. Okay, see, almost very same question, just a small change in the data. Just only a small change in the data I have done here. Rest it is a similar condition only. Okay, x1 dot x2 dot. x1 dot x2 dot. Okay, the x dot is ax plus bu and y equal to cx. Okay, now see, what is x1 dot, dear? Only x2. That means x1 coefficient is 0, only x2, and plus no input term. So here 0. What is x2 dot? Minus 2x1 minus 3x2 plus u. Okay, and what is y? x1 plus x2. Y is x1 plus x2. So both coefficients 1, 1. Again, CCF form, na? Same matrix 0, 1 minus A0 minus A1, 0 BU, y equal to C0, C1. Only C1 value changed. C0, C1 can be any value, na? Ultimately, the form is the same. Dear, this is also CCF form. So controllable. CCF form, so controllable. No need to check it. Now observability. I will check it again and then I will introduce the shortcut. Observability, I will check it again and then I will tell you the shortcut. Okay, observability, I will check it once again and then I will tell you the shortcut. Okay, so what is the shortcut for observability? First, let me check it. So for observability, we need the matrix V, which is C, CA, C matrix this time 1, 1. Okay, CA matrix, let me do this calculation here. CA matrix 1, 1 and A matrix again 0, 1, minus 2, minus 3. On multiplying, what do I get? First row, first column, 1 into 0, 1 into minus 2. So minus 2. Then 1 and 0. So this is 1. This is the result I get on multiplication. Correct? No, sorry. 1 and minus 3. So this is minus 2. First row with the second column. Okay. So let me write down these entries here. So minus of 2, minus of 2. Now what is the determinant of V matrix? Okay. Similar rows, proportional rows. Cross multiply minus 2, minus minus 2, 0. Determinant V 0. So the system is not observable. It is controllable form. It is CCF form, so controllable but not observable. Clear everyone? Clear everyone? Now see dear. Understand the shortcut for observability. Understand the shortcut for observability. Okay. Understand the shortcut for observability. Dear, from this particular equation, okay, state space equations, can I write down the transfer function? See dear, why not? Why not? I can use the same results. Now I've told you what I was telling you right now. If this is the transfer function, this is the CCF form. So again, vice versa, from CCF form, how to write down the transfer function? Let us use the same result. So guys, for the first example, I am writing the transfer function. Okay, I am writing the transfer function. First means actually this is the second example. The question prior to it was not in the CCF form. This is not CCF, not OCF. Okay, so hence we don't apply any CCF or OCF results. We have solved it normally by the Kalman's test, the full Kalman's test. But if it is CCF, I am telling you why to waste time. If it is CCF, it is controllable. Now see the transfer function, dear. Now see the transfer function. Now dear, what is this minus 2, minus 3? These are the coefficients of the denominator, opposite sign. So what should be the constant term? If here it is minus 2, here it should be 2. Then reverse 3s plus s square. Quadratic, na? Second order system. Then numerator, what is the common term? What is the common term? B is 1. Okay. And then y equal to C naught C1. C naught means the constant. Okay. 1. And next coefficient is 0. So 0 into s. Okay. So what is this? 1 upon s square plus 3s plus 2. 1 upon s square plus 3s plus 2. Correct, na? Transfer function is obtained. Let us go to the next. Then I will tell you how it is observable. Let us go to the second question. Let us keep relating. Second question, again CCF form, so controllable. No need to check controllability. Now write down the transfer function. Y by u equal to how much? Okay. Again, the constant of the denominator should be 2. Here minus 2, the opposite side 2. Then reverse 3s and then s square. Okay, b. What is b? The common term is again 1 into C0 and C1 both 1. So C0 1. Okay, plus C1s. Okay, so what is the transfer function this time, dear? Y is 1 into s, that is s plus 1. Y by u is s plus 1. Can you factorize the denominator? Okay, s square plus 3s plus 2 is actually factorizable as s plus 1, s plus 2. And then what happens? And then there is a pole 0 cancellation. Dear, if a system is given in CCF form, it is always controllable. And once you write down the transfer function, and if there is a pole 0 cancellation, it will be unobservable. That is what already we derived using the Kalman's test as well. It is unobservable. Clear? It is unobservable. If I go to the previous example, again CCF form, so it is always controllable. And then I check the transfer function, and then there is no pole 0 cancellation. There is no 0 itself. If there is a 0, then we check whether there is a pole at the same location or not. There is no 0. That means there cannot be any pole 0 cancellation. There is no pole 0 cancellation. Okay. So, dear, if the system is given in the CCF form, it is always controllable. Check the transfer function. If no pole 0 cancellation, it is going to be observable. It is going to be observable as we already calculated using the Kalman's test also. Clear, everyone? This is the shortcut. Okay, I repeat, dear. If a question is given in CCF form, it is always controllable, finish. If there is no pole 0 cancellation, it will be observable also. If there is a pole zero cancellation, it will not be observable. So you can totally skip the Kalman's test for CCF form as well as OCF form. OCF form means always observable. Okay, reverse. See, OCF is given always observable. If no pole zero cancellation, it will be controllable. If pole zero cancellation, uncontrollable. Okay. And that is why I revised you the CCF and OCF form, and I'll go to the DCF and JCF also. I'll go to the DCF and JCF also, but first tell me this answer. First tell me this answer. Okay, a third order. Now dear, on a 3x3 on a third order system, directly applying Kalman's is actually more time consuming. Directly applying Kalman's is more time consuming. Okay. This is a third order system, correct? This is a third order system. Okay, so even if you want to apply Kalman's, it is lengthy. It is definitely going to be lengthy. It is definitely going to be time consuming. We can apply 100%, but it is going to be lengthy. Okay, so what to do? What to do? Have a look into this form. Have a look into this form, dear. Okay, so see, is it again a CCF form? Now see, last row minus A0, minus A1, minus A2. Okay, first column zeros and then identity matrix. 0, 0, B, U, or U or V, anything named to the input. Y equal to C0, C1, C2. Correct. Okay, as per what I told you, this is just like this. This is just like this. Okay, the CCF form for a third order system. So yes, the given form is CCF. So controllable. No need to check. So controllable. What you need to check is the transfer function now. Y by U. Okay, transfer function. Now this will be the constant. Minus 3 written, the 3 will be the constant of the denominator. Go reverse, then 4s. Go reverse, 5s square, and then s cube. Cubic denominator, it has to be third order system. Then numerator 2. 2 is a common term. B2. Okay, then only 1, 0, 0. That means only C0. C0 means the constant term. Okay, next term is 0 into s. Next term is 0 into s square. Okay, so dear, okay, what is the numerator? Is only 2 into 1. 2 upon something. Is there pole zero cancellation? How can there be a pole zero cancellation? There is no zero itself. So it cannot cancel with any pole. Okay, so very clearly there is no pole zero cancellation. No pole zero cancels. So system will be observable. Now dear, if you want, you take your time. You apply the Kalman's. You will feel how much time does it take. You apply Kalman's, you will feel how much time does it take. But here you can save your time. Okay, by these simple shortcuts, you can save your time. Yes, correct answer is A, correct, Anay, correct, Hovant. The correct answer is A. You can save your time 100%. Okay, CCF, so controllable. No pole zero cancellation in transfer functions, so observable. Done, finished. Not only you're saving time, you're actually saving a substantial amount of time. A substantial amount of time. Done? A substantial amount of time. Okay. Next question, another one. Okay. Okay, again see. Minus A0, minus A1, minus A2, first column 0, 0, then identity matrix. It is the CCF form again. Okay, again it is given in the CCF form, so it is controllable. Again, the conclusion for controllability is ready. It is controllable. What I now need to do? It is controllable. So what is the transfer function? Next calculation, again I do the transfer function. Y by U. Next, 9s square. Next will be s cube term. Now, constant of the numerator 1, common of the numerator 1. C0, C1. Now C0 is 2. Go reverse. Then 1 into s. Then 0 into s square. Okay, so that means what is the transfer function this time is s plus 2 upon s cube, 9s square, 26s plus 24, correct? S plus 2 upon S cube plus 9S square plus 26 S plus 24. Now there is a 0. But how to know pole 0 cancellation occurs or not? Because remember, okay, you cannot calculate all the poles. Oh. You cannot calculate all the poles. Is the video working fine? Hello, 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 hello. Just a second. It looks good. Why does it hang? Just a second here. Okay, you cannot calculate all the poles. Now looks good. Hello, 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 hello. Yes, yes, yes. I think it's back to normal now. Some connectivity issue was there. All good now. Yeah. So now you don't have scientific cubic calculators. In the GATE virtual calculator, you cannot solve the cubic equation. You don't know all the poles. So how can you comment pole 0 cancellation is there or not? How can you comment whether the pole 0 cancellation is there or not? How can you comment whether the pole 0 cancellation is there or not? Okay, how can we comment? So dear, I will just do one thing. 0 is known to me. S equal to minus 2. 0 is known to me, that is S equal to minus 2. Clear? Okay. Now, is there a pole at minus 2? Is S equal to minus 2 also a pole? Because I can't solve the cubic equation in the exam, how to check whether S equal to minus 2 is a pole or not? Simply substitute S equal to minus 2 in the denominator. Okay. Simply substitute S equal to minus 2 in the denominator. Minus 2 cube plus 9 into minus 2 square plus 26 into minus 2 plus 24. Dear, please complete the calculation. It will turn out to be 0. Please complete this calculation. It will be turning out to be 0. And because it turns out to be 0, that means S equal to minus 2 also satisfies denominator. So it is a factor of denominator. And also S equal to minus 2 is a root of denominator. That means S equal to minus 2 is pole also. Okay, is pole. Okay, that means because same location pole and 0, so pole 0 cancels, and because pole 0 cancels, unobservable. So this time the system is controllable but not observable. A basic thought you have to give on how to confirm the pole is there or not. Plus 26 into minus 2 plus 20. Okay. Some connectivity issue is happening. I don't know where the issue is. Let me just check the settings again. Yes, dear, I think the signal is going red again and again. Yes, 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 yes. Some settings Our settings here are all fine. Maybe some internet issue. Some internet issue, guys. Cannot help at this moment. Lot of dropped frames. Yes, 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 yes. Okay, I think now it is back to normal. Let me try once again. I think it is back to normal now. Okay, now next year. Okay, next is the Gilbert's test. Okay, next is the Gilbert's test for normal forms. Okay, next is the Gilbert's test for the normal forms. Okay, I'm observing again. I hope now it is back to normal. Okay, but if there is another issue once again, let's see what can be done now. Yeah, in between dropped frames have been there. Okay. Yes, yes, now definitely okay. Now definitely okay. Chalo dear. Okay, please observe. Now Gilbert's test for normal forms. And normal forms, I told you there are two normal forms. Again, it went bad. Okay, I'm observing again. I hope now it is back to normal. Okay, but if there is another issue once. Connectivity issues. Yes, guys, it is fluctuating. Red to, it's continuously going red and green, red and green. Okay, so it's fluctuating. I think we cannot continue this way. There are connectivity issues, and we'll plan another session for Gilbert's test. Unfortunately, I'll have to stop and we'll have to plan another session for the Gilbert's test. No, no, Raj, it is not manageable also because it's totally hanging. That doesn't make sense to continue that way. Just hang and hang and hang. Let's do it with better quality, I think. For Gilbert's test then. I think even this message, how much it is going or not. Okay, I think my message is clear to you. We will plan another session. Just acknowledge if you have got this message at least. Okay, because then it is totally fluctuating. Till now, we've received at least 10% drop frames. Okay, I hope this message is clear to you because Gilbert's test is again important and the simplest way to solve for DCF and JCF questions.